When I try and tell my family what I do, they don't really get it. So this presentation was born out of how I usually describe to everybody. And the way you make a wafer is exactly the same as you make a cake. Bake it. So today we're going to go through and we're going to bake the wafer that Isaac showed us earlier. And this is my recipe book. This here is our microwave detector, and as Isaac said, it catches the light and allows us to see space. So what do we mean by fabrication? It's the process of engineering a really small detectors on silicon, and that allows us to see very faint signals from space. And it's really necessary in modern astronomy, right? Because we want to see all sorts of different wavelengths. And these fabrication techniques I'm going to show you today are the type of thing that you also get when they're making a phone, or your laptop, or computer. So, what are we making here today? Well, Cardiff, we're known, specifically AIG, is very known for something called an MKID, Microwave Kinetic Inductance Detector. None of those words actually mean anything, but we pretend to do. And these detectors basically are made up of tiny little resonators. And our light goes in, and it kind of catches a wavelength, and it bounces around, and then we go, yeah, we've got that one. And that means that we can see things. This was Herschel, and this was a millimeter, sub-millimeter telescope. Oh, and this is what I'm making. This is something I designed, by the way. Don't hold your applause, it's okay. So, what to do? Where do we start? Well, first we start with an idea. Usually that comes from my supervisor. Then we go into research. I've got to pretend that I know what I'm talking about. We move over to simulation. Actually, we've got some very good simulations that I don't write. And they kind of do all the physical properties and the way things work, and we give it a good shot. I do some CAD, that was the picture you saw earlier, kind of make a quick design on a computer. And then I have to write a recipe, just like a cake, and then we move on to fabrication. And if it doesn't work, I go back to the recipe. So as a quick table of contents, I'm going to bring you out in the kitchen. I'm going to introduce you to the clean room, that's where I work. With deposition, we deposit our materials. Patterning, I'll make it look nice. Development, I'll make it actually nice. And then etching, we'll take away everything we don't want. And this is my kitchen. It's a clean room. It's very clean. We all dress up like minions, and it is very difficult to tell who anybody is when you're all wearing the same clothes to work. What makes it a clean room? Well, what do we need? We need full PPE, so that's the full gowns that we saw earlier. They're actually to protect the work on from us as much as it's protecting us from them being the wafers I'm working on. Laminate airflow, that means there's a constant airflow going through the room. There's little holes in the floor to then drop keys. And that just makes sure that we're recycling dust. No approved materials, again cardboard, no dust please. And then we've got chemical damage, gas pipes, hazardous gas alarms. It is quite a dangerous place. There are acids and there are plasmas and things do go boom. We at Cardiff has an ISO 6 clean room. It's at the bottom here. It's actually quite good. I just didn't have enough space on the page. But this basically says how many particles, little bits, you can have of what size, and they go up to ISO 1. We've got ISO 6, so we can have 293 particles that are larger than 5 micrometers. Deposition, putting down the first layer. We do start with a silicon wafer, very smooth. We buy those in, and that's because everything works with silicon because semiconductor switches on and on, blah, 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 blah. But this is one of the pieces of equipment I use. I don't really know how it works. There's about 5 buttons I press, and as long as no red lights start flashing, then I'm good. So, what do? Well, we vent the chamber down to atmosphere. We put our wafer into the chamber. I've got a nice picture here. One of these little wafers up here. And we want to get everything out of there, all the oxygen, all the gases and whatnot, because what we do is we run a program recipe that, don't worry about that. Basically, we heat up a material. We heat up metals. There's a couple of different ways we do that. We do it thermally. If you have something gold, it's very soft, it's very easy to evaporate. And you just splurt it everywhere, and you hope some of it gets on the wafer. And the other way is to do an E-beam, which is an electron beam, which is basically a laser that you curve onto it. Stuff like titanium needs a little bit more energy to warm up. And it just goes all over the place. and we have these sticks. There's actually a little crystal that we can actually measure how much it goes down. It's really important to get the right stuff. It's a little picture my friend Mary did. This is actually lots of little different materials, and they kind of spin around, and then you can select which one you want. Patterning. So you've got to imagine I've got my wafer. It's full of aluminium. It's all over the place, hopefully smoothly. And then we're going to start putting this goop on it. It's called photo resin, and basically it is a plastic that reacts to light. What we do is we drop it on with a little pipette, and we spin it real fast. And by spinning it, we can kind of decide what thickness our resistor is. The angstrom is a really annoying unit, kind of how thick an angstrom is. But for example, if I'm spinning at 5,000 RPM and I'm moving, let's say S1818, then it's about 25,000 angstroms thick. And that's how we can kind of, again, it's really important we get exactly the right sizes and everything. And then once it's all covered, we'll sort of stand it all up. We put it in an MLA. And an MLA is basically scans the whole thing with a laser, kind of like your laser printer, and it makes the stuff that we want either more polymerized and less soluble. So it kind of allows us to start thinking about patterning it. Oh, this is actually a real picture. It's not a real picture. The real picture that I use, and we use a lot in PhotoLith, and it just describes kind of a cross-sectional area of how our wafer looks. So far we have our wafer, our silicon wafer at the bottom here. We've got our metal, so that's the thing that we just deposited, and now I've just spun all this goop on it, so it's keeping it smooth. Development. I've lasered it, but I've actually got to get rid of the bits that I don't want. So we dunk it and stuff. Let me go back. We dunk it and stuff. I've lost a few this way. And when we develop it, we put it in a beaker, and it kind of washes away all the stuff we don't want, and we kind of end up with these walls. These walls are actually kind of important. As I said, what we're doing is we're trying to capture light. So every little micrometer of distance that we're getting or losing, right, that's going to actually change what wavelength of light. If I leave it in my water, in my developer for a bit too long, and that gets too big, then suddenly I'm getting blue light, and I'm looking for red light, and that really sucks, because then my supervisor hits me. Here's some of the profiles that we can get. Here's some of the profiles that we can get. You guys been drinking tonight? Here's some of the profiles we can get. We could use it for different things. This is actually an SEM, a scanning electron microscope picture. They're really, really small. I think these are really cool. They come with paint total. Then, once we've got it patterned, we want to etch it. We want to actually take away all the metal and bits that we don't want. And this is what it's oxygen is like lavender. When you heat different gases up, they get different colours. Oxygen is kind of lavender look. I think it's probably something else like argon, which makes it a bit more purpley. And there's loads of different types of, well, okay, there's two types of etching. There's wet etching and there's dry etching. Wet etching is you put it in acid. It's kind of nasty. I have to wear a really big gloves for that one. And dry etching takes loads of time, and I've got to put it in a big chamber that blows. Sure. There's different reasons why you might do both of these. Wet etching is really, really quick. I just pop into one of my cupboards and I just start dunking. And as long as I get the right amount of time, it's usually fine. Obviously, I want the right acid for the right material. It changes the way that it etches, and it allows really high throughput, so I can do loads of them in one go. Dry etching is a bit more of a pain. But it's something called anisotropic, which means it only etches in one direction. Wet etching kind of etches every direction. Dry etching is a little bit more kind of precise in that way. And it's got higher selectivity. So you can actually kind of decide a lot more what you are in our etching. You've got both layers and got both different metals. And I want to etch some things and not etch other things. Sure, that's enough. That is my picture. You can see we started to etch away the metal here. Oh crap, we're done. It's baked. Here's the picture. We've patterned it. And I forgot what slide this was. We've patterned it. This is something that I made in the lab. I think this one's got some resistor and this one doesn't. And you can kind of see it's aluminium, which is shiny, on top of silicon, which is also shiny. So it makes it very difficult to see. But here we go. And this is kind of my design. This is a one-layer wafer. These are a couple of resonators. So it's not like a full thing that we saw earlier, but it's starting there. I'm only 3 years into my PhD, don't mind. So we're getting there. And but if you did a foam, right, or you did a proper detector, there'd be loads and loads of layers, and you know, like again, if you're phoning a laptop, these can end up with like hundreds of layers. Like ICPM, they have like recipes that just go on and on and on. You just put it into a big machine. How long does this take? Well, deposition takes about a day. I've got to put it in, I've got to clean it, I've got to put it in, I've got to deposit it, I've got to take it out, and they kick me out the lab. Spin coating real quick, I just drop some goop on it, spin it around real quick, stick it in the MMA, takes about half a day, and then I kind of finish up some development. Usually I'm cutting it and they're trying to kick me out the lab at that point. Etching, again, honestly takes half a day. If I'm doing wet etching, it's really important that I know exactly what's going on. I don't want to cover myself in acid. If you do cover yourself in acid, you have to completely strip off and jump in the shower, which is a bit embarrassing next to your co-workers. And then you kind of clean and dice it. So you actually, you know, on that one, there was like 6 chips. You might have like 1,000 chips. And sometimes you've got to chop them up so you can put them in the cryostat, because as Isaac showed us, our cryostat's not that big. Oh, wait a minute, there's a hair. I forgot to wear my hairnet. Your hair is about 80 microns thick, right? Is that important? How much is that going to affect our wafer? Well, this is something that I made earlier. I didn't know this one actually. But you can see it's about 80% of this. So this, a hair along here, is just going to destroy all of these devices. And these devices. This is actually an LED, I know which one this one is. It's a quantum LED. But you can see what's happening. We can get very, very small. The smallest I've ever done is a micron. I didn't make these, but I made something that was a micron big. These are like capillaries wide. And you can even get even smaller. Yeah, these little hexagons. And these are actually some pictures that were taken in the ICS, the type of things that are built just around the corner. Thank you very much. Any questions? Yes?
How many of these are you churning out? Are you putting on a big sale, or are you just focusing on one statement piece?
Yeah, I'm just focusing on one kind of moment. I need to do it like once and right. I did work in industry for a little bit, and I was just churning them out. I was just making as many as I could, and I was giving them away for free. But in Cardiff, it's kind of a do it once, do it right kind of situation, right? We're in academia, so everything that I do, you know, that's not the end of the process, right? Once I've done that, I actually have to put it in a box so we can read off all the information, and then I take it up to the lab and I put it in our cryostat, and then I have to pretend I know what's going on with the cryostat, which is the thing in itself, and then I've got to get all the data off it, and then I've got to pretend I know what any of the data means, and then I've got to write a paper on it, so I'm only doing one, right? Because if I did loads, I'd be here for years. Anyone else? Yes, sorry, in front?
With like the different, I'm not sure what stage it is, but the like interactions,
Mm-hmm.
I think it was, is that just your knowledge, or is it you've got like digital support on what type of?
Which one specifically, sorry?
Sorry, I'm not sure what stage it is, sorry.
Was it during the making of it?
Yeah.
So I had deposition, which is deposited the stuff. I've got patterning it, which is with the laser, and I've got etching it, which is taking all the stuff off.
I think there was like quite a few like different, but it may have been this one, yeah.
Yeah.
Is that just like your knowledge of knowing how to
Oh.
which?
Yeah, I mean, there's lots of like stuff available online. Like, to some extent, sometimes I think this is more of an art form than it is a science, because you've got to get a real feel for it all, and there's little loads of tips and tricks. But for the most part, yeah, like a lot of these ways of doing it have been already developed. I'm able to look online and read papers and kind of try and look for similar things. It tends to be if you have a certain material that you want to use, and it's a bit tricky, someone else has usually done it. Right? Actually, one of the things we're looking at the moment is completely new. I'm hoping to get a paper out of that if it gets done. So I mean, we're in academia at the forefront, and sometimes you come across an issue that hasn't been done before. That's why I'm here, and that's a lot of fun to do. But yeah, there's a lot of good resources out there for it. Yes, at the back.
So the etching and the laser, how accurate is that? What sort of error ranges are you dealing with?
Okay, that's a good question. So with the lasering itself, you get down to about microns. I think you can get down. I think we comfortably do about 5 microns in our resolution. I'm actually put it down to a micron. I don't think we can do much more than that at Cardiff. There are some really, really fancy pieces of equipment that can go smaller. People with real money can go much, much smaller. There's something called diffraction lithography, something like that, and that allows you to get much, much smaller. And obviously, if you want to break into those real quantum effects, not that we're not messing with some quantum effects, but if you want to break into some real weird ones, then yeah, you want to go real, real small. So there is stuff out there for it. And then yeah, the developing and stuff, that will shift and change your resolution as much as you can. Yes? Yes, the back end?
So, when you apply the photometallic coating and then you dunk it in acid, how do you get those little divots and why does it not dissolve uniformly?
I'm sure you're talking about the divots in the very last picture? Or?
The diagram on the screen now, like those.
Yeah.
That's like when you get those dunking in an acid, right?
Yeah.
When you dunk it in acid, why doesn't it dissolve uniformly? Why does it make it thick?
Oh, okay, well, because this is a nice picture and it's actually a lie. Wet etching causes all sorts of issues. You get things like footing, and that's one of the things. I've got these special words here. Isotropic means it etches in every single direction. If you do it anisotropically with plasmas, then actually you can just physically force it off. You just go at it like a shuttle. Whereas wet etching, you're trying to dig in away at it. So again, it's a good question, but it really depends on what type you use and then how you use it, what metal you're using. But yeah, it's very rarely this uniform. I don't think I can give you another question. Does anybody else have a question? Yes, Chris.
How often does Pete hit you?
Not enough.
Blink twice if you're safe right now.
Yes?
You know the clean room?
Yes.
You know if you went into like an ISO 1 clean room,
Yeah.
do you have to, like, can you breathe in that? Do you have to because you said like not many particles. Like,
Yeah. No, so particles are like dust, like anything that's not oxygen. To be fair, at that level, ISO 1, you're probably talking like a biological clean room. So you might be talking respirators at that point. Yeah. I should probably leave the stage. One last question? No? Okay, we're good.
Okay.